Hi there, in this video we're going to go over the impulse function, also known as the Dirac delta function. Now the idea about this is, if we have an axis in time and with an origin, then this function will have an infinite height, but the width of the function will be infinitely small. Okay, so there's a couple of criteria here. The first one is we can say delta t equals infinity when t equals 0. We also say it equals 0 when t doesn't equal 0. Okay, so it means it's only defined at this point 0, and there's no definition, there's nothing outside, and at that point it's infinitely high. Now, one other part of the definition is that the function is normalised, meaning the area under the function is being set to 1, so we can say the integral from minus infinity to infinity of the delta t equals 1. Now, we note from that it's been integrated from minus infinity to infinity, and we've got a value, so this function delta t is an even function. So it can be generated by any even function. So let's say, for example, we generated this by a square wave. So if we draw a square wave here, then this distance here, we make that distance epsilon. So the height must be 1 upon epsilon in order to make that area normalised to 1. So it's 1 upon epsilon times epsilon, which equals 1. Now we could also, well, you notice that if we were to then make this epsilon, if it's half the distance, if we halve the distance, in order to keep the area the same, we must double the height, and if we halve the distance again, we would have to double the height again. And you can see that as the limit as epsilon tends towards 0, we'll end up with a function that's infinitely small in width but infinitely high in height, okay, which is the delta function. The same could be said for this triangular. If we take the triangle and decrease the distance here, we'd have to increase the height, and if we kept decreasing the distance, we'd have to keep increasing the height, till eventually as epsilon tended towards 0, this would tend towards an infinitely high function but of infinitely small width. Now the same could be done with the sinc function. If we take our sinc function here, okay, and then if we change the crossover point, so the crossover point became closer and closer to 0, eventually we'd end up with a sinc function that is extremely narrow but extremely high, and as the crossover tended towards 0, we would tend towards our limit, which would be our function, which is infinitely small in width but infinitely high in height. Okay, so we've summarised that there really by saying that if we take the limit as epsilon tends to 0 of an even function, then it would tend towards this function delta t. A couple of interesting things on delta t. If we look at the delayed impulse, so if we say the integral from minus infinity to infinity of delta t minus tau, then if this is the t-axis and that's our origin, then this distance here would be tau, so that point there would be tau, and it would be equivalent to taking this delta function and just shifting it up to this point here, tau, okay, and you can see that it's minus whenever you shift in this direction, because this function here is defined as infinity when t equals 0, so in order to get that to 0, we would have to say, for example, if that was 2, tau was 2, then it would be 2 minus 2, which would bring it back to 0, which would be a point for our definition. So if we were to take tau and it was on the other side here, then we would have delta t plus tau. Okay. Now the sifting property, if we were to take the shifted impulse function and multiply it by another function, then we would have the integral from minus infinity to infinity of delta t minus tau by d tau, which we know that by our previous definition here, that the area of that is equal to 1, but it would only be defined at that point tau. So if we are taking that and multiplying it by some function t, then that's equivalent to taking that value of 1, which only exists at that value tau, multiplying it with the function. So the function would go to 0 outside here because this is all 0, that's all 0, and it would only exist at that one point. So at that one point there, the value of f of t at that point would be the value of f of tau. Okay, so that's a sifting property. It just sifts out individual values of a function. Now, we're going to go over a couple of examples here. I've also got some out in Matlab, so you'll be able to see a few things in Matlab as well. So what we're going to look at here is we're going to look at taking a square wave in the frequency domain and doing an inverse transform to get it into the time domain. Okay, and then we're going to look what happens whenever we allow this function, which is a square wave there, to extend off to infinity, and we're going to see how that affects the function in the time domain. Now we're going to do the same thing, but we're going to do it in the frequency domain. We're going to do it in the time domain. We're going to take a square wave in the time domain and see how what happens to the function in the frequency domain. The reason for doing this is we can see how the impulse function is generated, and we can look at the forward and inverse transforms of impulse functions, and we'll be able to see the duality of the Fourier transform, which is really just an offshoot of the fact that the e to the j omega t is a symmetric function. So let's start here. If we have a square wave, okay, so there's a little square wave there, just to there, and we call that point there, the cutoff point there, omega L, and that minus omega L, sorry, and that other cutoff point there is omega L, and we make the height of that 1. Now before we go through the analysis, I'll just go through and tell you the answer. We know that that generates a sinc function, and the sinc function, the crossover points are multiples of pi upon omega L, and the height is omega L upon pi. Okay, now what we can think about what we're doing here is we're taking this function here, and that's a real even function of time, and we've seen from a previous video that a real even function of time, when you do the inverse transform, will give us, so a really even function of frequency, when you do the transform of it, will give us a real even function of time. Now this here is the inverse transform, so we're going from frequency to time. Okay, so that's taking a function. Okay, so in this case the function is just the height 1. Okay, but we'll take the function and we're multiplying it by e to the j omega t. Now e to the j omega t can be written as cos omega t plus j sin omega t. Now that's an even function, cos omega t, and that's an odd function, sin omega t. So if we took some function, you know, in that instance it's 1, but we'll just put a random function f of j omega. So we'll put some random even function. So we'll have an even times an even, which will give us an even, and when we integrate it, we'll get an actual value. If we have an even times a sine function, which is an odd, we'll have an even times an odd, which will give us an odd function. If we integrate an odd function from minus infinity to infinity, we end up with 0. So that won't produce anything. Okay, so that e to the j omega t, we're only actually using part of it, so it's only the cos omega t part we need for an even function. So we can draw out that cos omega t surface. So if that's omega there, and that's t there, then we can draw that surface out, and we can actually bring it up. If I really look to see here, I do have it somewhere, cos omega t surface. Cos omega t surface, yep. That's it here. Just bear with me while I get it into here so you can see. I believe, yeah, I think you can see that there. Okay, so that there is the cos omega t surface. Now if I shove it round like that so that it's in the same, looks the same, there you go. So that's the same way. So we're looking at the frequency here and the time here, and we'd have our square wave running up this axis here. Okay, so the square wave comes along, then say it comes up here, and then comes down here, heads along here. So outside this bit here, we're just multiplying that by this surface, and it would just be 0, and outside this bit here would just be 0, and the only bit of the surface would be this bit of a square wave, and we would just be multiplying it by 1, so we'd just be in effect cutting this surface just along like that. Okay, and then we would integrate it with respect to frequency, so that's, we're integrating it in that direction there, and when we integrate it in that direction, we'll get a sinc function in the time axis. Okay, so that's the time axis there, and the time axis up here. Okay, so that gives you an indication. Now, if I'll bring this back here quickly, let me draw what it says. So I never mentioned before, but if that wasn't an even function, if that was a purely odd function, then we wouldn't be multiplying it through the cos omega t surface. We'd be multiplying it through just the sin omega t surface. okay. But we have a sine omega t surface that looks very similar, okay, as again I showed you in a previous video, so I won't bother bringing it up there. So it means that we'd modulate that surface and then we'd integrate again in that direction to get the function of time. Now if we had a function that was both even and odd, then it would be more complicated because we would be modulating two of the surfaces, and then we would have to take those two modulations and then we would have to add them together, okay, the real and imaginary parts together in order to get your function of time, okay. But we're not going to go through those complexities, okay. It's just to give you a graphical indication. So that's us had a kind of thought experiment, and we've seen how we can find this inverse transform. Now here's the actual inverse transform. Now it's a bit kind of bookwork, and you can always pause it and just have a little look through it yourself, but we're taking the inverse transform here, okay. So we're trying to find the time domain from the frequency domain. So the function is just 1, so that's just the function 1 times e to the j omega t, so it's going to be 1 upon 2 pi. Now we're integrating with respect to omega, so the j and the t just look like a constant, okay, so we end up with 1 upon jt e to the j omega t, and the limits are from plus omega L, okay, that's our omega L there, to minus omega L, which is that point there, okay. So we could take the 2 down in here, and when we take the 2 down in here, we multiply by omega L upon omega L, then this whole function here, this part here, is going to look like the sine omega L upon sine omega L upon t, and when we take the omega L in here, okay, that's our omega L here, and we've got the omega L up here as well, so we end up with this function here. So if we've rewritten it out, it's f of t equals omega L upon pi sine omega L t upon omega L t. Again, just pause that and you have a little look at it, or you can find it really in any signal processing book. Now a little identity here, that function there, sine omega L upon omega L t, it's of that form, sine x upon x. Now when we take the limit of x tends to 0, sine x upon x, that equals 1. Now I'm going to go through a video of that and I'll put it in the snippet section, okay. Now that's not defined at x equals 0, so what we can do is we can call that function a sinc function, and we can define that sinc function as equaling 1 when the value of t equals 0, okay. So that's a definition, and there's a little proof of that in another part of in the snippet section. So now what we're interested in is these height, that height there, and that crossover point, okay. So the height, first of all, a couple of ways of doing it. We can say the limit as t tends to 0 of their function, okay, so we take it as t just tends to 0, and we take the limit of that function there. Now we already know the limit of that function because it's the same as that here, it equals 1, so the limit of that function there will just be 1, will be 1 times omega L upon t, so we just omega L upon pi, so we'd have omega L upon pi. The other way we could do it, we could just look and we could just say, well, we've defined sinc of 0 equaling 1, so because it's sinc of 0 equals 1, that whole thing there just equals 1, so we have omega L upon pi times 1 is just omega L upon pi, okay, so that just gives us the height. And the crossover point, now our contention is that the crossover point here is pi upon omega L, so we're really saying it's 0 there at pi upon omega L and minus pi upon omega L, okay. So what we can do is we can put pi upon omega L for t into our function here, okay, and just check, make sure that equals 0, so we end up with omega L upon pi times sine omega L times, well, t now becomes pi upon omega L, and the same at the bottom would be omega L, and the t would become pi upon omega L. These would cancel out, these would cancel out, you just end up with the sine pi here. Now we know that sine of pi is just like saying the sine of 180 degrees equals 0, okay. So it means the crossover points occur at integer multiples of n pi upon omega L, okay. Now what we're interested in doing here, and the reason for doing this, is that if we were to take this square wave here, okay, and we were to extend it out, okay, and keep extending it, so omega L would become larger and larger and larger, okay, so the cutoff point would become larger and larger, and as it tended off to infinity, then this function here would just look like a straight line, just of height 1, okay, that would go on to infinity, in both directions. Okay, so if that was a case of omega L tended to infinity, then really just from our graph here, as omega L tended to infinity, then that pi upon omega L will tend to 0. So we're saying that crossover point will tend to 0. So the sinc function will get tighter and tighter and tighter and tighter, okay, and that will tend towards 0. And obviously the height there, well, omega L is tending to infinity, so that height there is going to tend to infinity. So we can see then that this function here is going to tend towards an impulse function. We're going to have a function there that's going to be a infinitely small width but infinitely high height. Okay, now that's what we noted here. Okay, that's all we really said here. Now, given that's the case, so we've now redrawn that. We'll say, right, okay, we'll let that tend off to infinity, so that just becomes 1, and we'll let this tend towards the sinc function, so we end up with a sinc function there. Okay, now if I was to find the Fourier transform of that sinc function, so I'm looking at analytic, well, I'll do it, just think about it first of all, and then we'll look at it analytically. We'd be taking that function, right? That function would just be modulating that surface, which I've already shown you. Now, it's 0 all the way along here, so it would just make the surface 0. 0 along there, so it makes the surface 0. The only point exists just at that one point there when the t equals 0. So when t equals 0, we know it's a cos omega t surface, so cos of 0 would just be 1, so it'll just be a height of 1. Okay, so when we integrate it, we're integrating it with respect to time, so we're just looking in along that axis. So if we look along that axis, what do we see? We'll just see this value here of 1 all the way along. Okay, so that's a simple graphical representation of the Fourier transform of an impulse function, and it's quite obvious when you look at it like that. Now, if we were to do it analytically, we would just have the Fourier transform of delta t, so with delta t e to minus j omega t. Now, we know that that doesn't exist other than when t equals 0. Okay, now when t equals 0, the value of that is just going, the area under it is just going to be 1, so in effect you'd be multiplying 1 by, and this here, whenever you'd integrated that there, the limits of integration, well, the limits of integration are just going to be 0 and 0 because it only exists at point 0. Okay, so you'd just be literally equivalent to saying e to the minus j omega and t would be 0. Okay, so e to the j 0, right? So n raised to the power 0 is 1. Okay, so you would just have a value of 1 there. Okay, so that's a first transform pair. So you take the transform of an impulse, you'll get 1, and that's what you say. We take that, transform that impulse, and the forward transform of that impulse will give you 1. Okay, so that's the first part of it. What we're going to do is we'll go on and we'll look at it in the other direction. Okay, so we'll take the square wave and we'll put the square wave on the time domain, and then we'll look at the sinc and the function and the frequency domain, and we'll let our value of our in this case it would be t tend off to infinity in both directions, and we'll see that becoming a sinc function, and then we'll look at it and we'll see the Fourier inverse transform of a sinc function in the frequency domain. Okay, so let's just crack on, we'll go on with that. Again, we'll see some of these in Matlab, okay, just a few images just to show that it does actually work. So in this instance here, we've got a time here, okay, and we've got a function of time, and that function of time is just a square wave, and we can say that the cutoff, we'll call the cutoff tau by 2, and that cutoff there is minus tau by 2, and again it's a real even function, so it will produce a real even function in the frequency domain. Now we have this square wave here modulating the surface, okay, in the same way there's a square wave here modulating the surface in that direction, because the surface is symmetric, you end up with the same thing. That square wave modulates that surface, and then whenever you integrate it in that direction, you end up with a sinc function. Okay, so that really shows you the symmetry of the Fourier transform really comes about due to the symmetry of e to the j omega t function, and also is determining whether your function here is an even function or odd function or multiples of those. Okay, so again, we'll just go through it, and let's say it's the height 1. Then before we do the analysis, I know that that crossover point occurs at 2 pi upon tau, and that height there is tau. Okay, so now here's the proof of it here. So we're going through and we're doing a forward transform, so it's an integral from minus tau upon 2 to tau upon 2 of the function. Well, the function is just the height 1. Okay, so it's 1 times e to the minus j omega t by dt. Okay, so we're integrating with respect to t, so j omega just looks like a constant, so you end up with minus 1 upon j omega e to the minus j omega t, from tau by 2 to minus tau by 2. So that is minus 1 upon j omega e to the minus j omega, and t gets replaced by tau by 2, and again minus t gets replaced by minus tau by 2, so that ends up with a positive there. And if we take the negative sign here in, so we multiply, that becomes negative, that becomes positive, we end up with the ej omega tau upon 2 minus e to the minus j omega tau by 2 upon j omega. Now we can multiply the whole thing out, the wee trick that we used, multiply it by half tau upon a half tau. When you do that there, this thing here is the sine a half omega tau, okay, and this becomes a half omega tau here. Okay, so that's our function there. Okay, so that's us worked out what this function here is. Right, so that's the analytic version of that function. Okay, now if we, again, we're looking at the crossover point and we're looking at the height. Okay, so when omega equals 0, right, so omega equals 0, we're looking for that height there. Well, when omega equals 0, we know that, again, it's the sinc function. Okay, so the sinc of 0 is just equal to 1. Okay, so we're going to end up with the value here is just going to be this whole thing is the sinc function, just be 1 times the tau here. Okay, so you'll end up with the height is just tau, and again the crossover, our contention is the crossover is 2 pi upon tau, and the same as in the previous one, we'll just put 2 pi upon tau in here. Okay, so we end up with a t tau sine a half, and omega gets replaced by 2 pi upon tau, and again omega gets replaced by 2 pi upon tau here as well, and when you cancel them out you end up with a sine pi here, and again sin pi equals 0. Okay, so that proves that's a 0 point, and those will occur at integer multiples n 2 pi upon tau. Okay, now the same thing we're going to do here, we're going to let tau tend towards infinity. Right, so if tau tends towards infinity here, well, that height tau there is going to tend towards infinity, and this crossover point 2 pi upon tau tends towards 0, so we're going to, if tau tends towards infinity in that time axis, then this is going to tend towards a function that's infinitely narrow but infinitely high, so that's the impulse function. And again, that's what we've noted that there, that's really just what I've said there, and we're going to end up with an impulse function now in the frequency domain, and we're going to end up with a value. Now the value is actually isn't 1, the value is actually 2 pi because of the value of 2 pi in the Fourier, the inverse transform. Okay, and if we were to look at this, and we can look at it the same way we did the previous one. If we have delta omega modulates this omega t surface. Okay, so it makes the surface 0 here and 0 there, and it only exists at one point there, so the cos of 0 is 1, so that would be a height of 1. So we integrate it then in that direction there, so we're just looking in for here, and what do we see? We see a height of, in this instance, a height of 2 pi. Okay, so that means that the Fourier transform over delta omega will just equal, well, it's actually 2 pi, it's actually 1 upon 2 pi. Okay, so that's we've seen it there now. So if we were to go and look at that analytically, we'd say the forward transform, so the inverse transform there of this function here is 1 upon 2 pi, the integral of the delta function, so it's delta omega e to the j omega t by d omega, and the exact same thing occurs here. We end up 1 upon 2 pi, that's being integrated with respect to omega, so the jt is would look like a constant, so you'd end up with 1 upon the jt coming down, but it wouldn't really matter anyway because it only exists at a point when omega equals 0, okay, and we know that the delta omega by d omega, the integral of that is going to be equal to 1 because that's by definition. So you just end up with 1 upon 2 pi e to the jt, and the omega there is just going to end up, will just be a value of 0, okay. So we end up 1 upon 2 pi times 1 is 1 upon 2 pi. So you end up with the inverse transform of delta omega is 1 upon 2 pi, okay. So that means that we take this delta omega and it will produce a value of 1 upon 2 pi, which is just a straight line there, okay, 1 upon 2 pi, going off to infinity in both directions. Now, you generally don't see it written like that. Usually what they do is they say, well, we'll take the 2 pi up here to the other side, okay, so we can say the Fourier transform of 1 is going to be 2 pi delta omega. Now that's us got to the end of that lot there, so what we'll do is we'll just look at the duality of the surface and have a quick talk about the usefulness of it. So if we took an impulse function and we found the Fourier transform of it, we would get 1. Okay, so that's the time domain, that's the frequency domain. If we were to take the Fourier transform of 1, okay, so that's the time domain, Fourier transform of 1, we would get delta omega, but it would be multiplied by 2 pi, so it's slightly out, so there's not an exact duality, but it's just slightly out. So it means that if we were to take the Fourier transform of this delta t, we get f of j omega. If they were then to take that again, so this function here is the same as this function here, okay, well that one's defined in the frequency domain, but if we had to define it again in the time domain and take another Fourier transform of this, so in effect we take the Fourier transform twice, okay, then we'd end up getting back to the same type of function we had at the beginning, but it would be slightly out, it would be out by a factor of 2 pi, okay, so that's what you see in the duality of that surface. So you can see as we go either end here, we've got the same functions, okay, we've got the same types of functions. Now, an interesting thing here is that if we look at this delta function, what we can say is we can say we're resolving in the time domain, meaning we know exactly where in the time domain that function exists exactly, but when we resolve that in the time domain, it means that in the frequency domain, it's spread out the entire frequency domain, okay? So narrowing a function in the time domain will spread a function in the frequency domain. And equivalently, if we've got a function in the frequency domain and we are able to resolve it exactly, so we know exactly what frequency it is, then when we resolve that in the frequency domain, when we go back to the time domain, that function is spread out over the entire time domain, okay? Now, they use that fact there, and they use it in quantum physics, and they use it in the uncertainty principle in order to describe the idea of a momentum and position not being able to be known perfectly at any point, okay? So that's why you'll see the Fourier transform cropping up in quantum physics. Just an interesting side. Now one last part, because there's another couple of things that we can get out of this, another couple of transform pairs. So if we look at the delayed impulse, so there's a delayed impulse, delta t minus tau. We're taking the Fourier transform of it, so we're just taking a time domain function and we're taking the Fourier transform of it, okay? And that's a delayed time, so that's a delayed impulse, and we're taking the Fourier transform of that delayed impulse, then we know that only exists when t equals tau, and the value of that will be 1 when t equals tau. Okay, so the integral then of e to minus j omega t, well, it only exists when t equals tau, so that's just the same as e to minus j omega tau. Okay, so the forward transform of that impulse is a function which is in fact just like a corkscrew. Okay, now we could do the same in the frequency domain. We could look at an impulse in the frequency domain, so that's the frequency domain. Okay, and we can delay the impulse in the frequency domain, and then we can look at it in the time domain. Okay, so we're taking a function delta omega minus v, so it's occurring at that point there, so that's the v point there. Okay, so e to the j omega t by d omega. So again, it's the exact same derivation we have up here. That only exists at v, and it'll be a value of 1. And whenever we do the integration there, again, the limits integration only exists at point v, so it's e to the j vt, and it's a factor of 1 upon 2 pi. Okay, so you'll end up with that 1 upon 2 pi coming up there. Okay, so we'll end up with e to the j vt equals, and that should actually say 2 pi delta omega v. Okay, so that's another transform pair, so that's a final transform pair. What I'll do is we'll go on and we'll just look at the examples in Matlab. Okay, but there's our transform pairs. Okay, so that's just what we've derived. Okay, so let's have a wee look at some of this stuff in Matlab just quickly. I'll give you a bit of an indication of what's going on here. Let's see if I can find out where is the recordings. So just bear with me while I bring this up. So I'll look at the sync function. Let's we found it. I'll bring it up on the screen here, Matlab. Okay, I think you can see that okay. Okay, so that's me looking at the sync function. I'm saying the sync function, you can see that there's the crossover point just about here. Okay, so that's the crossover point, and that's tending towards a square wave. So that's a square wave here, and it's the sync function of time. So this is the time domain signal, and that's a Fourier transform of that signal there. Okay, now as we extend this out and we make this value here our crossover point further and further out, okay, then this here will tend towards 1, okay, and this thing here will tend towards an impulse function. You'll be able to see that there. So I think I've got another couple that's 0.5. If I make it wider, 0.5, let's see this one here. That's maybe not the best one to give. Right, okay, so I suppose what's happened there is I've actually taken the sync function, and that is actually sync function. It'll come along like that, it'll come down, okay, and it'll come all the way down, because you can see the scale in that, okay. Okay, so it's just a huge sync function, right, and you see it tended towards an impulse there. Okay, I think I maybe had a... Okay, that's going the opposite direction. Okay, but it gives you an indication. Okay, and that's again there you go. There's a sync function that's extended out, and you can see the crossover point there is not down at 10. It's over at about 20. Okay, so as that is getting wider and wider there, it's tending towards an impulse function there. Okay, so it just gives you an indication that it does actually work. Let's see if I get any other impulse. Let's see, delayed impulse, surface unit impulse, delayed longer unit impulse. Well, actually, I think I've got an impulse delayed. Right, let me see here. Unit impulse now. So, well, there we go. So here's an example here. If I bring it up here, can I? let's see if you can see it on this Matlab. Right, I don't think you can see it there. Matlab window. There you go. So okay, you'll be with that's you. I think you've got it there. Okay, so there in the bottom line, that's a unit impulse. Okay, so it's an impulse, infinite height. Well, but you only show the area as 1. Okay, at 0, and it gives you a value of 1 off in both directions in the frequency domain. So that's the time domain, and that's the Fourier transform of it. Okay, so that's time domain, that's the frequency domain. Okay, so then if we were to delay that, I think this will be the last one I'll show you here because the video's been on a bit longer. So that's unit impulse delayed. Right, so there's a delayed unit impulse. Okay, so it doesn't actually show the impulse here, but the impulse, I don't know why it didn't show, but the impulse is not at the 0 point here. Okay, it's delayed slightly, it's further along here, and what happens is those, you can think about these, that was originally just sitting at a value of 1, but now all the phasors have started moving. You can see it shifting. Okay, it's actually starting to corkscrew. Okay, and you can see it a bit better if I delay it a bit longer, a longer delayed one there. There you go. So that's it delayed even further, and you can see it starting to corkscrew round. Okay, and I think I've got one more longest. There we go. Right. Okay. Right. Okay. Now I don't. There you go. So you can see it's delayed even further, and it's in the time in the frequency domain. It looks like a corkscrew. So the time delayed impulse will look like a corkscrew in the frequency domain. Okay. So I think that'll do. There's nothing else I want to say there. The next video I'll go and look at the unit step function. Okay, thank you. Goodbye.